So our first half on magnetism is finished. So basically magnetic fields and forces and charged particles, all of that is now done. And now we're moving on to the second part of magnetism, which is related to electromagnetic induction. So how basically electricity can be generated using some principles of magnetism, and this is actually what generates energy in real life as well. But before going towards that part, it's really important to understand the concept of magnetic flux. So remember that when we were talking about the magnetic field strength, we also used to refer to this as magnetic flux density. And now you'll actually know why this is so in this video, why magnetic field strength is also called magnetic flux density. So you may also remember this point about the magnetic flux density, which is that when we were talking about sketching those field lines, so we used to say that the lesser the spacing between the field lines, the greater is the magnetic flux density. Right? So this is how we used to qualitatively talk about magnetic flux density. Now, because we were just sketching those field lines on a piece of paper, we couldn't really understand this there, but you can think about it in this way as well, that if you have some magnetic field lines like this, which are going in some direction, and let's say there is some area, let's actually realign them for what I'm about to do now. So in 3D, the meaning for these field lines would be this, that the greater the field lines passing through some area, the stronger is the magnetic field strength, or what we call magnetic flux density. So we can probably guess that the magnetic flux density here is in turn the density of something called magnetic flux. So this is some magnetic flux per unit area. So then what we can do is, to get magnetic flux into the mix, we can say that if this is some magnetic flux phi per unit area, so phi is then the magnetic flux density times this area to which it goes perpendicularly. So how we define magnetic flux is the product of the magnetic flux density and a perpendicular area. So let me also, in light of this discussion, let me adjust this diagram a bit further. So maybe something like this is what the actual magnetic flux density would be, because this angle needs to be 90, right? So this is the product of the magnetic flux density and a perpendicular area. So let me also just add here that this perpendicular area is perpendicular to the magnetic field lines here. So let's say it's to the lines of flux. And what flux really means is flow. So when people first discovered magnets, so people had this idea that this is a flow of something. So basically, because they didn't really think about it in terms of magnetic field lines at the time, so that they just thought that this is some flow. So this is why this quantity is called. So then magnetic flux, you can just think of this as the total number of magnetic field lines which are passing through some given area. So that's why it's the product, because magnetic flux density is the field lines passing per unit area. So you multiply by the area again to get the total number of field lines which are passing through here. So the unit for magnetic flux is called the Weber, and this is abbreviated as uppercase W, lowercase b. And if you see in this formula, so 1 Weber, or it's also called Weber, so 1 Weber would equal to 1 Tesla multiplied by 1 meter square. So basically the unit of Webers is equal to 1 Tesla meter square. So you need to be very particular about this thing, that this is the area which is perpendicular to the magnetic field. So remember how I adjusted the diagram above? Well, what if I didn't adjust it? What if there was in fact some angle between the magnetic field lines and the area, as would be the case in a diagram like this? So the same diagram as we had above, but let's say now the area is not perpendicular to the magnetic field lines now. In fact, there is some angle theta between the area and the magnetic field lines. So again, you need to consider the component of the magnetic flux density which is perpendicular to the area. So in this case, you would resolve the magnetic flux into a cos and a sine component. So in this case, the expression would become phi equals to BA and a cos theta as well, right? Because of the B cos theta multiplied by the area A through which it passes. So let me also label this. So this is some area A. And the magnetic flux density is some B. So that's the idea of magnetic flux. And if we extend the same idea further to a coil then, so this is some coil and let's say it has N turns here and it has some cross-sectional area A. So all the coils are the same size. It has some cross-sectional area A. So we have the same magnetic field lines which are going through here. We make a couple of those. So you have these magnetic field lines going through this area. And again, the same thing, that the magnetic flux density is still B. So you can see that basically because of this many N number of coils, the actual effective area would also be multiplied by that much. So can I say that the area here, the effective area, would be the area of one coil multiplied by the number of coils we have? And then to find the magnetic flux, in that case, I would multiply it by this magnetic flux density. So in that case, what we call is not just the magnetic flux, we actually call it the magnetic flux linkage. And this is a term which is reserved for coils having some number of turns. So this really doesn't have any other special symbol for it. Because if we talk about magnetic flux linkage, so we know that the total magnetic flux linkage in this case would be BA, but also multiplied by the number of turns. So this is just called N phi, right? So the magnetic flux times the number of turns. So that is the magnetic flux linkage here, right? So phi was basically just BA. So N phi is N times BA. So let's have a look at an example here then. So this question says a coil is constructed by winding 400 turns of wire onto a cylindrical iron core. The mean radius of the coil is 3 centimeters. It is found that the flux density in the core due to a current in the coil is this much. Part A says calculate the magnetic flux in the core. So the core is just a normal cylinder which has some area. So there are no number of turns involved with the core. So for the magnetic flux linkage, phi is the magnetic flux density multiplied by the area perpendicular to the field. So B is 1.4 here, and the area is corresponding to 3 centimeters. So basically the area is pi r square. So 3 centimeters, so 0.03 squared. So this corrected to SF will turn out to be 4.0 into 10 to the negative 3 Webers. And you can also call this 4.0 milliwebers. On to part B, the flux linkage of the coil. So we need n phi now. So n phi. So we've already found phi. So 400 times that, 4.0 into 10 to the negative 3. So this turns out to be 1.6 webers. Right, so magnetic flux and the flux linkage have the same units. The flux linkage is a term which applies to coils having some number of turns, whereas the magnetic flux applies to any area. So in the next video, we'll actually build upon these concepts to talk about more advanced laws.